We'll pick up here where we left off with allowing for bone flexibility and tensile strength, the presence of the organic component, primarily collagen. Again, we typically don't think of bones being bendy, but in fact they are, and it's necessary that they do have a slight amount of bend to them to allow for the proper workings of our skeleton. Tensile strength refers to the ability for a bone not to stretch. You think, well, of course my bones don't stretch. Well, they don't stretch because of this osteoid being present. To envision what we mean by bone stretching, you would be carrying a really heavy suitcase and your arm bones would get longer. Well, we don't want that because over time, your knuckles would be dragging on the floor and that would be really a bad look for you. So by having this osteoid present, it keeps our bones durable and working in the way that we need them to be working. Next, we have the inorganic component, which makes up 65%, obviously. 35 and 65 will give us that 100%. This is made up primarily of calcium and phosphate, our good friend phosphate, in the form of something called hydroxyapatite. Hydroxyapatite is a very, very complex chemical formula. What we need to know about it is it's made up mainly of calcium and phosphate, and it gives the bone their characteristic hardness that we need it to have to be that rigid frame for our body. As I said, we're going to have this slide about suffixes to know, and here we are. The suffix blast refers to a cell that creates a tissue's matrix. And again, remember, matrix is the material, not cellular. It's made by the cell and it surrounds the cell. It's all of that other stuff. If you think of the areolar tissue, you had cells, but you also had those fibers. The fibers are part of the matrix. The cells are not. The cells are what produce that matrix. An osteoblast is going to be a cell that's responsible for producing the matrix of a bone. Chondroblast, the root chondro refers to cartilage, so a chondroblast is going to be a cell responsible for producing the matrix of cartilage. And a fibroblast is a cell that's going to be responsible for making the matrix of fibrous connective tissue. Now we have a site. A site is going to maintain that tissue's matrix. We've already talked about an osteocyte, right? So we can have an osteocyte, we can have a chondrocyte, we can have a fibrocyte. Which type of cell is going to determine which type of matrix is going to be created or maintained or ultimately broken down. And that's where the clast comes into play. This is a cell that destroys a tissue's matrix. And again, osteoclast, chondroclast, fibroclast. Whatever the root is talking about is going to be what that cell is going to break down. Ossification is the process that bone is formed by osteoblasts, those cells that are responsible for making the bony matrix. Ossification is the process by which bone is going to be formed. This is going to include the creation of both organic and inorganic portions of the matrix. The osteoblasts are responsible for making both types of matrix, and they're both necessary for the process of ossification to occur. Ossification begins during the 6th or 7th week of development in utero, inside of the mom while she's pregnant, and continues throughout adulthood. There are two types of ossification. We can have intramembranous ossification, which is going to occur within membranes, and endochondral ossification. Now that we know the root chondro is cartilage, endochondral is going to mean that it's going to occur within a cartilage. Important points about ossification. Before we go too much further, we've got to talk about some things that relate to both types of ossification that we've got to kind of keep in mind when we're talking about how this process occurs. First is that both cancellous and compact bone come from both types of ossification. cancellous bone is that spongy bone that we talked about that we're going to find in the bone ends in the epiphyses. And the compact bone is what's going to be on the outer covering of that and also what makes up the diaphysis, the shaft. Both types of that bone matrix is going to come from both types of ossification, both endochondral and intramembranous. Our life would be a whole lot easier if we could say, okay, cancellous comes from this one and compact bone comes from that one, but that's not the case. Both types of ossification make both types of bone. Next, the process of bone deposition is just about the same. What this means is, whether we're talking about intramembranous or endochondral, the process of ossification occurs in just about the same way. To make it even more confusing, the bone matrix formed from one type of ossification is exactly the same as the other. What I'm saying is, if we were to collect bone matrix, some that was made through endochondral, some that was made through intramembranous, and analyze it and get the chemical composition, they would be virtually identical from one another. We would not be able to tell one from the other because chemically they are exactly the same. Although bone is formed from pre-existing tissue, the bone replaces that pre-existing tissue. So, if we're talking about intramembranous, we're talking about the pre-existing tissue being a membrane. Endochondral, the pre-existing tissue is cartilage. What we're saying here is we're going to start with a pattern, right? A template, if you will, of membrane or cartilage. And as the bone is formed, that pre-existing tissue is going to be broken down and all that will be left behind is bony tissue. Something important to remember is the processes we are discussing occur during embryonic development in utero before you're born, where undifferentiated cells are plentiful. There's lots and lots of cells who have not been given a specific job or task yet. That means they have the ability to change their plan, kind of like a freshman in college who's not really sure about their major, right? They're just kind of floating along going, I'm not sure what I want to do. That's what these undifferentiated cells have the ability to do. So when you're reading and talking about this process of ossification, you've got to realize that we have cells that haven't been determined yet. They haven't gone down a path yet, so they can change what they're going to become. Let's talk about intramembranous ossification. This is going to be ossification that occurs within a membrane. It's going to be responsible for the formation of flat bones, some irregular bones of the skull, and the clavicle. So we have a very specific knowledge of which bones are going to be formed through intramembranous ossification. Some irregular bones of the skull, the temporal bone, the sphenoid, our good friend the ethmoid. Okay, so those are going to be examples of bones in the skull that are made through intramembranous ossification. Intramembranous ossification is going to begin with a collagen membrane that is formed during embryonic development. Because again, remember, we're talking about the process of making bone that occurs within an embryo, within the mom. We can contrast this with endochondral ossification. This is responsible for the formation of the bones at the base of the skull and most of the remaining skeleton. So if we didn't mention the bone specifically for intramembranous ossification, it's going to be formed through endochondral ossification, including but not limited to all of the long bones in your body. It's going to begin with a hyaline cartilage template. Template is a fancy word for a pattern. A stencil, if you will. If I want to make perfect circles, I'm not going to try to do that freehand. I'm going to cut out a piece of cardboard that's a perfect circle, and I'm going to trace that. That's a template. So we're going to use this model, this stencil, if you will, to plot out what our bone is going to look like, and that's going to be made of hyaline cartilage. Ossification is going to begin at the primary ossification center. This is located in the middle of the template. That will become the middle of the shaft or the diaphysis of the bone. It will then continue at secondary ossification centers, which will be in the epiphysis, the ends of each of the long bones. Ossification continues until the only remaining cartilage is going to be found in the epiphyseal plates and the articular surfaces. That's where we want our hyaline cartilage to remain, because the epiphyseal plate is going to allow for continued growth, and those epiphyseal plates will ultimately ossify at skeletal maturity. The articular surfaces are the areas where the bone meets bone, and we want that hyaline cartilage to cover the surface so that the bones do not grind on one another. And again, here are my favorite pictures. We have our epiphyseal plates in place. All right, so that's where we're going to find our hyaline cartilage. Ultimately, that will be gone when the individual reaches skeletal maturity. Now I'm going to sound like your mother yet again. Nutrition is very important when we're trying to make or maintain anything in our body, specifically talking about bones. Good overall nutrition, having a balanced diet, eating our veggies, all those things that moms tried to drill into your head all these years, is actually necessary for bone formation and bone to remain in good working order. Specific to bone, though, let's talk about a couple of different vitamins. First, vitamin D. It's necessary for calcium absorption from the intestines. So here's the deal. If you don't have vitamin D, you could be taking buckets of calcium, and it's not going to do your body any good, because that calcium, for the most part, is going to pass through your intestines and out of your body. With vitamin D, it allows calcium to be absorbed from the intestines. Without enough vitamin D, the bones will lack calcium. Bones that lack calcium will lack hydroxyapatite. Hydroxyapatite is the inorganic part of the bone that gives the bone hardness. So the bones will not have the necessary hardness that it needs if it does not have enough calcium, because it doesn't have enough vitamin D. Vitamin C is next. Necessary for normal collagen formation and mineralization of the matrix. So we need vitamin C for both the organic and the inorganic portion of the bone matrix. Without enough vitamin C, the bone is going to be brittle due to the lack of collagen and somewhat mineral deficient. Hormones. Clearly, we would need the growth hormone for bone formation, because that's what helps your body make new tissue, make new whatever it's trying to make. It's going to act on the epiphyseal plate to stimulate growth. This growth hormone is active during infancy through childhood. And I know you all don't want to hear it, but even though you're college students, you are still, for the most part, considered to be in childhood. Childhood goes through, adolescence, which is part of childhood, goes through until 18, 19 years old. And that's typically where we see skeletal maturity, where our epiphyseal plates are converted to our epiphyseal line. Sex hormones are also important in bone formation, specifically testosterone and estrogen. They are most active at puberty. That's when you get that jolt of sex hormones. They're going to stimulate bone growth. This is why typically, along with puberty, you get a growth spurt, as we call it, this kind of shooting up in height, because you now have sex hormones added in with the growth hormone, and it's going to cause your bones to grow at a more rapid rate. Conversely, it's also going to stimulate ossification of the epiphyseal plate. So it's kind of a twofer. Not only does it cause growth to be accelerated, it's also going to ultimately stop growth by causing the epiphyseal plate to be ossified. In our next lecture, we'll begin talking about diseases of the bone.